Let's get started. Hi everyone, my name is Xiao Chen from USC. Today I'm going to talk about Caesar for cross-camera complex activity detection. This work is in collaboration with UCSB and ARL. Let's get started. Today the camera has becoming the most powerful and most ubiquitous sensors everywhere. They could be fixed, they could be on someone's body, it could be on drone, and it could be equipped with a GPU on set. And these camera feeds can be used, can capture many meaningful activities. For example, in Las Vegas shooting event, the shooter got captured taking luggages many times with a lot of luggages to his room. If someone could capture this activity from the surveillance, maybe this tragedy could have been avoided. Similarly, the camera's feeds can also be used to detect other actions like traffic accident, and more recently, companies like Amazon, they started to use surveillance cameras to capture the people's shopping activities to enable their Amazon Go, cashier fee shopping. But today's activity analytics is highly manual because there are so many videos and so many concurrent video feeds that this guy is sleeping. So what's the solution? We should replace this sleeping guy with a software, right? So our ideal case is that we have a piece of software that monitoring a cluster of cameras with heterogeneous inputs. On the other side, the user can tell this system to keep an eye on some specific actions, like a person gets into a car, then gets out and walk with a bag. Once the system captures these actions, it will return the related frames so the people can get alerted and do some subsequent operations. Okay, let's look into detail about the user-defined action. You can see this is a pretty long sequence, and we call it to be a complex activity. On the contrary, we also have a concept of atomic action, which is, you can see here, they are just some smaller pieces, smaller components of a complex activity. So far, there's no prior work on this complex activity detection, but there are already many atomic action detection in both the system community and the vision community. And Caesar will be the first to fill the gap. Here is an example to show the difference between complex activity and this atomic activity. We have two cameras here, and there's a guy being captured. He first uses phone, then he takes a bag from someone else. Then he travels to the second camera, gives the bag to someone. In existing work, we can accurately detect these atomic actions, like use phone, take bag, give bag, associated with different cameras. And this is an example of complex activity. A person uses phone, then takes a bag and gives a bag. You can see this complex activity is cross-camera, and it could involve multiple persons and multiple objects. Before going to complex activity, let's look back to today's approach for atomic action detection. The first step is object detection, which is given a video feed and the detector outputs the bounding box of each object in these frames. The next step will be tracking. Given the bounding box of objects, the tracker will form the same person's boxes into a tube, and this tube describes the person's movement in the current time. And the next thing will be action detector. They get feed from the different tubes, and for each of the tube, the action detector will process the frames and output the most probable actions that happens currently. Today's most popular approach for action detection is deep neural nets. It is trained with a large data set that contains a lot of video clips and human labels on it. On the left side, you can see we have use phone, talking, reading, a lot of different actions. And once the model is trained, it can be used to test in the real time. We can feed it with a tube, short tube video, and it will output like the use phone with a high confidence. But the problem with today's DNN is that it requires training data. It is true that as long as we have good training data, it can detect various different atomic actions with very good accuracy. But for complex activity, which have multiple tubes and longer sequences, we have rare like such training data for that. Even though we can have this data, we still need to train a separate deep neural net for very specific complex activity. This will be a total overkill, and it will not be generalizable at all. Then we come up with, then we find a more ancient approach that when in the area there's no deep neural net, people will simply just use the tubes to infer what the action could be. For example, here, the two persons get closer, their tubes move closer to each other. And people used to define some simple rules to capture the action like two persons getting close. But the problem with this approach is clear, that because it doesn't capture any detailed pixels context within those boxes, so it can detect very limited types of actions. But the good thing with rules is that it's very intuitive, it's very human friendly, and also it's generalizable to describe a wide range of relationship between multiple tubes. So our basic idea for Caesar is to combine these two together. In Caesar's rule, here is an example. In Caesar's rule, we cover both the deep neural net generates actions and also the simple rules actions. You can see here a person's skateboarding moves with a person riding a bike. You can see this complex activity cannot be detected by either just the DNN or just the simple rules. So that's where Caesar will be able to detect much more types of complex activities. We have a few goals for Caesar. First, it should be flexible to enable the user to define their own complex activity. But how to do that? Then it should be scalable, which means for many concurrent video streams, it should not feel sleepy. It should not use too much hardware resource. And also, because we want to support mobile cameras, we want to save energy and wireless data. And these are three challenges. Let's look at the first one. How we can define these rules and detect it accurately. First, in Caesar, we provide the user with this vocabulary. Like here, you can see these atomic actions. They could from different source of detectors. On the left, it is re-identification neural net. In the middle, it will be some simple rule-generated atomic actions. On the right, they come from the DNN that generates a bunch of atomic actions within a tube. To combine this, to describe this relationship between actions, we also involve the spatial relation and logical relation. They will be used like a natural language to organize all of these simpler actions into a more complex shape, like this example. So a user wants to define like people use phone, then move with bag. Then we can use the above vocabulary to form a graph like this. Let's see how Caesar works with an example. First, the user inputs the action definition to the system. The grammar is like this: the action name, the subject's variable, and the most important, the action definition. At the bottom, you can see it's like natural language, and different atomic actions, they are connected with logic connectors. In the backend, Caesar will parse this definition into a graph. At the runtime, Caesar will process the tubes frame by frame and try to match that graph. Whenever one node in the graph is matched, it will be marked as red, like this. As time goes on, once this guy is captured, like moving and whiz back, this graph will be fulfilled, and Caesar will output a positive result. Let's look at the second contribution, the scalability. To understand what scalability means, let's first take a look at what's the bottleneck that we faces. So from our experience, like most of the system's overhead comes from the deep neural net. In Caesar, we use 3 deep neural nets. The first one, object detection, and also the re-ID deep neural net, and also the action detection neural net. We can see that the action detection neural net is the most heaviest part. It is 50 to 60 FPS per tube. That seems fine, right? But it depends on the number of persons in a frame. If there's a frame that has 10 persons inside, the FPS will drop like a lot, right? Not mentioning that we have like a lot of concurrent videos at the same time. So then the key is how can we optimize the action detection DNN execution at runtime. We have the insight that in the previous graph definition, actually we can classify those atomic actions into 2 categories. The first part is simple rule generated actions, like stop, move, getting closer, disappear, blah, blah, blah. And another type is DNN generated. The second type must require DNN to run to get those actions. So we have an idea. Instead of running, matching the graph frame by frame, how about we just first try to match all those simple rule actions? Because those nodes doesn't require GPU to run for the action DNN. So here is the workflow. In Caesar, it first tries to match all the green nodes in a graph, and once it finishes all the green nodes, it will go back, try to match whether there's a red node can be matched. Only at this time, Caesar will output the result. Let's take the previous example. Okay, so first step is the same. We will try to detect not with bad, but at this time, we won't try to detect useful. Then we try to finish all the remaining graphs because all of them are just simple rules. Only at this time, we will go back to search for previous tubes to see whether this guy used to use phone before. And you can see here, only at the very last moment that Caesar will run this action DNN for the chain. But in the strawman approach, if we don't use that, we have to run the action DNN for every frame. For the third contribution, efficiency, we also have the insight that instead of asking the mobile camera to upload every single frame, we find that actually it doesn't have to be. Because for the previous rule-based atomic actions, it only needs the bounding box positions instead of the pixels. So most of the time, the mobile just needs to upload the bounding box positions with 4 integers, not the full image. And only when we require the action DNN to run, that we will query the mobile to upload the content within the bounding box. And if we have more bandwidth or we want to do visualization, we will query the mobile side to upload the full frames. This is the logic on the mobile side. By default, the Caesar will just upload the bounding box and cache the image and boxes. When the server finds that it needs box images or full frames, it will send a query back, and the Caesar mobile will upload the images. This is how Caesar looks like. We have a server that controls a bunch of mobile nodes. The mobile could run on a laptop or like mobile GPU, like NVIDIA TX2. In evaluation, we run the Caesar mobile on 8 NVIDIA GPU boards. They are connected with Wi-Fi. Caesar server runs 3 NVIDIA GPUs. And the data set, because there's no existing complex activity data set, so we use a pedestrian detection data set called Duke MTMC. It captures 8 videos from different parts in Duke campus, and we have 30-minute video in each camera. In total, we manually labeled more than 1,000 atomic actions, and we found there are 149 recognizable complex activities, and most of them are cross-camera. Overall, Caesar could achieve 61% recall and 59% of precision. And we find that all these errors are due to these 3 causes from DNN. The first part is object detection. It can't detect anything. The second one is tracking. The re-identification across camera is wrong. The same person no longer belongs to the same person. The third one is the failed action detection. And if we replace the DNN's output to be the ground truth, we can see the Caesar could achieve accuracy to be 100%. That means those action graph algorithm is perfect. For the scalability, we compare Caesar with its strawman version, which doesn't have lazy matching. So we can see that in this red line, the strawman's FPS drops a lot as the number of cameras increases to 8. But if we apply this lazy matching concept, for most of the actions, it will always keep the FPS more than 15%. And for those spatial-only actions, which means those atomic actions only generated by simple rules, and Caesar could keep the FPS more than 17. For data usage, because the mobile just need to upload the box most of the time, so like it saves a lot of mobile data. And also on the right side, you can see because the Caesar have lazy matching, so it becomes much faster. So the mobile doesn't have to wait, so it will run much shorter time than the strawman, and also saves energy. Here is the demo video I want to show. So first, in this topology, there are 2 cameras along one street. We can first see this person use phone, then he meets with someone that just gets out of the car. The output of Caesar is at the top of these videos. And you can see the Caesar can detect these taking back actions like at real time. And then the same 2 people appear in this another camera, and this like giving back action is also detected. In the second topology, we have 3 cameras covering the different parts in a plaza. You can find many cross-camera actions and also ready-back actions. And the third one, we have a drone that's flying in a shopping mall plaza. You can see Caesar still works by detecting like actions like getting off cars. Because we don't have 2 drones, so that we can't show a cross-camera on drones, but by default, they're the same. So here is like my talk, and we published our code on GitHub. Now I'm ready to take questions. Thank you.
Thank you.